On July 12, 2022, we saw the first set of images from James Webb. The Carina Nebula, SMACS 0723, WASP 96b, the Southern Ring Nebula, and Stephan's Quintet. We're now exactly 100 days since those first 5 results were released. It's time for an update. Hi everyone, I'm Fraser Cain. I am the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. Now, back in early July, we gave a detailed description of all of the cool first images that came out of James Webb. But as predicted, the telescope has been working non-stop, producing many images. We've been reporting on them every week on Universe Today, here on the YouTube channel. But if you want like one place to hear all of the updates, this is the video for you. All right, let's get into what we've discovered with James Webb in the first 100 days of operations. It's important to understand when you think about Webb, what are the primary science objectives? What are the purpose of this telescope? And it really has four main categories that it's going to be looking for. It's looking for the end of the dark ages, the first light and reionization. It's looking for the assembly of galaxies, the birth of stars and planetary systems, and the origins of life. So when we talk about all of the images and observations and data that's been gathered so far, keep those in context with the larger goals of James Webb. We're also going to give you an update on how the telescope is doing itself and what does the future hold, what other observations are planned for cycle 1 and into the far future with James Webb. All right, let's get into it. Changing our understanding of galaxy evolution. Webb is an infrared instrument, which allows it to see wavelengths that other telescopes have a hard time seeing. It can see well beyond what the Hubble Space Telescope can see into the far infrared. And when we're looking into the universe is expanding. Objects which were once visible light have been red-shifted out into the infrared end of the spectrum, beyond the reach of the Hubble Space Telescope, but Webb can see it. We've had infrared telescopes before. We've had the Herschel Space Telescope, we've had the Spitzer Space Telescope, but to be able to see into the far infrared with such a large telescope allows us to see very faint objects seen just a few 100 million years after the Big Bang. And so one of these first major objectives of Webb is to be able to look at the early universe, just a few 100 million years after the Big Bang itself. Within a few weeks of those first images that we saw, we started to get releases of other galaxies seen at incredibly high redshifts. And the redshift is the rate that the galaxy is speeding away from us, and that translates into times when the light was released. Now, for Hubble, it was able to see galaxies that were about, say, 600 million years after the Big Bang. Webb has been able to find galaxies that are around 250 million years after the Big Bang. And this is a very important time because this is the time when astronomers think that the first large galaxies started to come together and form into the larger structures that we see today. It was expected that you would see these small irregular galaxies at the beginning of the universe, and then over time, they would form into larger and larger structures. But what Webb saw was that even at around 250 million years after the Big Bang, like when these galaxies are just starting to form, they're already surprisingly mature, more like disc-shaped galaxies, the kinds of galaxies that we see in more mature times in the universe. And that was a surprise. Not only were the galaxies surprisingly mature, but the stars are surprisingly mature. Back at the beginning of the universe, everything was hydrogen with a little bit of helium and some other trace elements. Anything beyond that is metal, according to astronomers. And it was expected that these first galaxies would be made of mostly much lighter elements. But actually, what astronomers found was much heavier elements. They found things like oxygen, which are only produced at the hearts of stars that are in the end stages of their life. And so what that means is that even at 250 million years after the Big Bang, galaxies were filled with stars that contained heavier elements. The stars had gone through many cycles of birth and death, going into supernova, releasing heavier materials that seeded other star-forming regions, which led to new stars being formed out of those heavier elements. But strangely, when you get to cosmic noon, which is about 3 billion years after the Big Bang, the expectations were reversed. And so astronomers were expecting during this period, this is like the point of the largest star formation. This was like, if there was a time when the universe was the most exciting, the most star formation, it was about 3 billion years after the Big Bang, cosmic noon. But with the Hubble Space Telescope, astronomers saw these large, mature galaxies, and they expected that that was going to be the case, that all of the smaller, irregular galaxies had merged into the bigger galaxies, and we're moving on to this more mature time of galaxy structure. But with Webb, they were able to reveal all of the fainter galaxies mixed in with these larger, brighter galaxies. And in fact, the story is a lot more complex, that there's still a lot of less mature, dimmer galaxies mixed in with these bigger, brighter galaxies. And so what this is all leading to is that the formation of galaxies in the early universe was more complicated than astronomers were originally expecting. Was it that the galaxies formed first and then the supermassive black holes formed in their center? Did the galaxies come together as small dwarf galaxies merging into larger and larger galaxies, or vice versa? The story is becoming more complex. Not the Big Bang was wrong complex, but at least you're seeing finely nuanced arguments for and against different methods of galaxy formation, and more research, more data will be able to fill in all the missing pieces. You can imagine this time in a few years when astronomers have this really firm foundational understanding of how we went from the first stars in the universe through the early stages of galaxy formation, through the cosmic noon when you had all of the star formation going at its maximum amount, and then leading to the mature grand spiral galaxies that we have today, and eventually into the elliptical dying galaxies that we know we'll see in the future. Another puzzling mystery in astronomy are globular clusters. Now, we see these ancient clusters of stars surrounding most galaxies. There's a lot here in the Milky Way. And what's weird about them is that they are not in the main disk of the galaxy. Instead, they are mostly randomly above and below the plane of the disk. And so they probably didn't form with the galaxy itself. They came from somewhere else, some other galaxy. Were they the heart of a dwarf galaxy that was pulled out and all of the stars were extracted and was added to the mass of the galaxy, and yet the heart was still left orbiting around the galaxy? We still don't really know, but we do know that these things are old. The age of a globular cluster can be almost as old as the universe itself. And we got new images of globular clusters, or proto-globular clusters, from James Webb. Now, this wasn't a direct image of the clusters. It was done using gravitational lensing, where you had a foreground galaxy that was able to act as a natural telescope lens for some background galaxy that contained these proto-globular clusters. But Webb was able to detect very high rates of star formation in these objects, which shows you the time when these things probably still formed. Now, this is a very complicated, very difficult observation to make. More research is necessary, and I'm sure over the coming years, more and more of those pieces will come in. But for me personally, I really like globular clusters. To know where they came from, to be able to watch them coming together near the beginning of the universe is really exciting. Now, I'm sure many of you are here for the exoplanets, not the galaxies, or maybe you want both, but for those of you who want to know about the exoplanets, we got a lot of information. In that first data release 100 days ago, we saw this really interesting spectral signature of the atmosphere of WASP 96b. And this is a planet that contains water vapor in its atmosphere. That's cool. And not just like there's probably water vapor, but a really clear signature that there is absolutely water vapor in the atmosphere of this planet. And then a month later, astronomers announced that they had detected the presence of carbon dioxide in the atmosphere of another exoplanet called 39b. Now, we see carbon dioxide in the atmosphere of planets here in the solar system. There's a very thin carbon dioxide atmosphere at Mars. There's a very thick one at Venus. So this is a common chemical to see in the atmosphere of a planet, but it has never been conclusively seen in the atmosphere of another exoplanet. And yet, with James Webb, astronomers got this clear, unambiguous signal that there is absolutely carbon dioxide in the atmosphere of this planet. You wouldn't want to live there. It is like a Saturn mass-sized planet, and it's very hot, orbiting very close to its star. But still, the detection of carbon dioxide is very exciting. And over time, we're going to get more and more signs of different chemicals in the atmospheres of different planets. And speaking of chemicals in the atmosphere of a planet, astronomers were able to detect the presence of silica in the atmosphere of a brown dwarf. Sand. And is this normal? I mean, brown dwarfs are also called failed stars. They're very hot, but they're not star hot. They're not going through the regular fusion process in their cores. They're going through a kind of fusion where they're burning deuterium in their cores, but not full hydrogen to helium fusion. But they do put out a lot of heat, and clearly that's hot enough for them to have silica, sand, in their atmosphere. Overachieving planet. Yeah, it's an overachieving planet. Yeah. All right. Now, the analysis of the exoplanets is mostly done using the transit method. You're watching as the planet passes in front of the star. You're detecting the chemical fingerprint of the planet when it's in front of the star and when it's not in front of the star, and astronomers are able to tease out which are the parts of the planet. But Webb is sensitive enough, and it has a coronagraph on board that can block the light from the star, that it's able to image planets directly. And we got to see a photograph of an exoplanet taken by James Webb. This isn't an Earth-like planet. You're looking at a planet that is about 9 times the mass of Jupiter, and it's orbiting around an A star, which is a much hotter, more massive star than the Sun. And when you consider the brightness of the star versus the planet, it's about a factor of 10,000. In other words, the coronagraph on board James Webb is able to dim the light from the star so much that it's able to see the image of the exoplanet. But it was able to use several different filters on board James Webb to be able to reveal the planet over and over and over again. And astronomers were able to study this direct light coming from the planet. Now, to actually be able to see an Earth-sized world orbiting around a sun-like star at around the distance of the Earth, you need to dim the light by about a factor of 10 million. So Webb can't do that. But if you want to learn more about coronagraphs and the technique that will take us there, I did a really fascinating interview with Dr. Lucy Lebeau. She shows an actual coronagraph, and we talk about what it's going to take to be able to image another Earth around a sun-like star. So we've talked about Webb looking out to the edge of the observable universe. We've talked about it looking at exoplanets, but Webb can look inside the solar system too. And it has been hard at work imaging some very familiar objects. One of the first images that we saw was Jupiter. And astronomers using Webb pointed at Jupiter because that's a fairly fast-moving object in the solar system, and they wanted to test how well the telescope can track objects that are moving that quickly. They were able to successfully image Jupiter, take a bunch of images, and it wasn't a detailed study, but because Webb is a far infrared telescope, it was able to show Jupiter in wavelengths that we just don't get to see very often. In addition to really detailed images of the cloud tops and the storms and the Great Red Spot, it also showed the auroras on the north and southern pole of Jupiter, which are just these faint, ghostly halos above the planet. We also got an image of Mars. And this was a pretty tricky image because Mars is one of the brightest objects in the sky, especially right now as we're recording. Mars is fairly close and very bright in the sky. In order to be able to see Mars, astronomers had to take very short exposures of the planet and then stack them up to be able to get all of these interesting faint details. One of the really cool things that they did was a spectroscopic analysis of the atmosphere of Mars. And we know, we have spacecraft at Mars orbiting around on the surface. We know the composition of the Martian atmosphere very well. And so Webb was able to do a scan of the atmosphere from its orbit, and from there able to produce a spectroscopic signature of the chemicals that are in the atmosphere of Mars. And this is very helpful. It's a method of calibration, which then we can know as Webb starts to see similar kinds of atmospheres out there in the universe, compare them against the work that it's done here on Mars. So it's very useful to do calibration. And probably the coolest picture that we got of the solar system was of Neptune. We've never seen Neptune in this wavelength at this high detail ever. And really, we haven't been close to Neptune since the Voyager spacecraft did a flyby in 1989. And it was able to discover the ring system, some of the moons around Neptune. And so here in this image from James Webb, you can see the dusty rings orbiting around the planet. You can see one of its moons. You can see the storms in its atmosphere, which are varying amounts of brightness. And it just shows that we need to send a mission back to Neptune. There's so many mysteries to uncover there. One last observation that is interesting, and that is that Webb participated in the observations of the DART mission. And this was where a spacecraft crashed into asteroid Dimorphos, changed the orbit of this asteroid, avenging the dinosaurs, and the world's telescopes, both on ground and in space, were observing the impact as it happened. Webb was staring both before and after the impact for about 5 hours of total observation time. It was able to produce 10 images that astronomers were able to use to study the after effects of the DART impact. And what's cool about this is that it teamed up with the Hubble Space Telescope. This was the first time that Webb and Hubble imaged the same object at the same time. I'm sure there'll be more partnerships in the future, but it was pretty exciting to see the two great telescopes working together. And this was another challenge for Webb because the asteroid was moving so quickly. And so the techniques that they figured out on being able to image on Jupiter, they were able to apply those lessons to imaging the DART mission as the impact happened. But maybe you're here for the pictures. And there have been a lot of really beautiful pictures. We saw the Carina Nebula and the Southern Ring Nebula in that first release of images 100 days ago. And in the Carina Nebula, you can see the powerful stellar winds are pushing the gas and dust, forming these giant cliffs, which are many light years across at a level of resolution we've just never seen before. It's a stunning image. I'm sure it's already the background image for many of your desktops. A few months after that, we saw the Tarantula Nebula, and this is one of the largest star-forming regions in our region. It's actually located in the Large Magellanic Cloud, which is about 170,000 light years away. And yet, some of the most massive stars that astronomers have ever seen are in this incredible star-forming region. Like it's really hard to get across the scale of the size of the Tarantula Nebula. It's mind-blowing. And with Webb, which is able to see through the gas and dust, you've got the perfect instrument to look at star-forming regions. In this image, you're seeing stars that had never been seen before because they were shrouded by gas and dust. That's the power of an infrared observatory. We've seen several galaxies captured by Webb, and the infrared view gives us a different perspective, showing the regions of gas and dust where the star formation is happening. So here's IC 5332, which is a galaxy about 30 light years away. And here's another one. We're looking at NGC 1365. And if you look right down into the center of this galaxy, you can see that it has an actively feeding supermassive black hole at its center. And we've seen a few more images from Webb that have this same tone. And when you think about the Hubble Space Telescope, you think about these really famous images like the Eagle Nebula, the Pillars of Creation. You've got this color palette. And that's the Hubble palette. And it's very familiar, very recognizable. And now as we see these galaxies coming out of Webb, they have this palette. And I think once again, you're getting this recognizable view to see these images and go, okay, that is a Webb galaxy picture. In fact, we put a whole bunch of galaxies and planetary pictures and nebula pictures head to head. We had a vote on our channel. And in the end, the viewers picked NGC 628, which is one of these galaxy images from Webb. So it really looks like it's one of your favorite styles of images as well. 100 days in. How is Webb doing? Well, we've got some good news and we've got some bad news. Now, the good news is that the Ariane 5 upper stage rocket that carried Webb into its orbit was flawless. The insertion was so good that Webb had to use almost none of its own propellant to get into its final operating orbit. And so it has many more years of life. Like originally, astronomers were hoping that it would end up with 10 years of time of propellant left in the tank, but it looks like it's going to have about 20 years of propellant left. And when you compare like Hubble, think about all of the observations that have been made with Hubble over 30 years, 20 years will be a pretty good run. Now for the bad news. It's taken a couple of hits. There have been a few micrometeorite impacts on Webb. Most of them have been nothing, completely well within the tolerances, but one was a little bigger than anybody was expecting, and it caused noticeable damage to one of its mirror segments. Now, it has 18 total mirror segments, and even on that one mirror segment, it's just a slight damage to the segment, and it can work around it, but you get this slight degradation of the total image quality. Still well within the boundaries that astronomers were expecting, but still a slight degradation. And I'm sure over time, as more impacts build up on the telescope, we'll see further degradation, but nothing that is going to take the telescope offline. And there's another problem. Engineers detected some excess friction on one of the modes of the MIRI instrument. And based on that, they've had to shut down access to that instrument on MIRI. So not the MIRI, the full MIRI instrument, just one of its modes. And they're still trying to troubleshoot, figure out what the problem, what's causing this excess friction. I'm sure they'll figure it out and then bring the instrument back online. But until then, all of those observations that were going to be using that mode have had to be pushed back until they get it operational again. That's 100 days. What's coming next? Webb is operating at almost full time, day after day after day. And there's some really cool sites that you can get to see where the telescope is observing. You can see just hour by hour what its targets are, what instruments it's using. And there's some really cool target, like just this week, for example, I took a quick look through. There's an observing run planned for Fomalhaut, which is a star that kind of looks like the Eye of Sauron. You're probably familiar with the star. Wouldn't you love to see the Webb version of this? I would. There's also time allocated for this bizarre galaxy called NGC 7172. Here's the Hubble version. I wonder what the Webb version is going to look like. But you can also zoom out one level and you can see all of the Cycle 1 papers that Webb is going to be participating in. There are dozens and dozens of studies, and they're broken up by stuff that is inside the solar system, outside the solar system, galaxies, star-forming regions, exoplanets, cosmology. Some of the papers in this list are going to be familiar. They've already gathered the data, and others we're waiting to see it come in. So, and that's just cycle 1. Like that's just the first year. 19 more years after this. And as the data reaches the 1-year mark, it gets put out into the public available archives, similar to what happens with the Hubble archive. You can go through 30 years of Hubble data and you can answer questions that you might have about space and astronomy, research exoplanets, look for asteroids, discover supernovae. It's all in there in the Hubble data, and you can go through it. We report on stories all the time where astronomers go through older Hubble data and make some pretty incredible discoveries, like plumes of water coming out of Europa or tens of thousands of asteroids being discovered. And so we can expect similar discoveries made in archived Webb data as well, as different teams of astronomers get their hands on the data and do their own analysis. 100 days. Here we are, just 100 days since Webb has gone operational, and we have seen so many incredible images of nebula, of exoplanets, objects within the solar system, galaxies seen at the edge of the observable universe. It's really exciting, and they're just getting started. We've got the rest of cycle 1 and then ideally another 19 years after this. And of course, I will keep you posted on every cool discovery that gets made by James Webb. So thank you. I hope you enjoy this overview, and I'm sure we will do it again. If you don't want to miss any of the news, you should subscribe to our channel. We release breaking news about space and astronomy every week, answer your questions, and interviews with researchers so you can learn a lot more. Just click subscribe. You can also get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There are no ads and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross who support us at the Master of the Universe level. All your support means the universe to us.